Hello, welcome back to module 14 of the course on pericyclic reactions and organic photochemistry. We are still in the cycloaddition stage only. This will be the last module on cycloaddition reaction, wherein we will consider higher order cycloaddition reactions. Until now, the cycloaddition reactions that we have discussed are only 2+2 involving 4 electron cycloaddition and 4+2 involving 6 electron cycloaddition reaction. Those are the most commonly involved cycloaddition reactions that we encounter in organic synthesis. There are cycloaddition reactions involving larger pi systems. Typically 8 electron, 10 electron, 12 electron and 14 electron systems are also known, but they are not very common in nature. The higher order cycloaddition reactions also obey the Woodward-Hoffmann rule, but there are certain differences that one can observe in the higher order cycloaddition reactions, which we will consider in this particular module. Here is an example of a 4pi cycloaddition reaction involving two molecules of butadiene in a phase-to-phase manner, resulting in a superficial cycloaddition reaction to give cycloocta-1,5-diene as the product. Now this reaction mechanism could be that initially a 2+2 cycloaddition reaction is formed involving the formation of a 1,2-divinyl cyclobutane derivative. The 1,2-divinyl cyclobutane derivative can undergo 3,3-sigmatropic rearrangement to still give the same product. So one cannot distinguish a 4+4 cycloaddition reaction from a reaction involving 2+2 cycloaddition reaction followed by a 3,3-sigmatropic rearrangement, which is a cope rearrangement to give this product. However, a more convincing evidence comes from this molecule, which undergoes 4pi cycloaddition reaction. If you want to visualize this particular molecule, this is like a roof-shaped molecule. Because of the cis fusion on the 9-10 position of dihydronaphthalene, this molecule possesses the shape of a roof, which brings the carbon number 1 and carbon number 8 as well as carbon number 4 and carbon number 5 in close proximity, such that a bond can be formed between carbon number 1 and carbon number 8. That would result in the formation of a 3-membered ring, which is this 3-membered ring in the product here. Similarly, the bonding between carbon number 4 and carbon number 5 will involve the formation of another cyclopropane ring, which is this cyclopropane ring here. So this is a true example of a 4pi superficial cycloaddition reaction. This is feasible only because of the fact this molecule has the necessary geometry, which is the roof-shaped geometry, which allows the overlap of carbon 1 and 8 and carbon 4 and 5. So such a facility is necessary probably for involvement of a 4 electron overall an 8pi electron cycloaddition reaction to give this interesting molecule, which is a polycyclic molecule in this case. 4pi cycloaddition reactions are also known in an intramolecular version. This is a intermolecular version of the one that we saw here is an intramolecular version. The one we see here is an intermolecular version of this molecule. This tetramethyl butadiene that is shown here, it is shown in the transoid conformation. It undergoes 4pi cycloaddition reaction between anthracene and itself, resulting in the formation of a cycloadduct. Please note the stereochemistry of the initially formed product that is coming from this reaction. This has to undergo a cycloaddition reaction in a transoid geometry to give this particular trans isomer of this olefin, which is in the cycloadduct. So the 9-10 position of anthracene reacts with the 1 and 4 position of the transoid butadiene molecule, resulting in the formation of this trans isomer of the cycloadduct, which is shown here. Under the photochemical conditions, cis-trans isomerization prevails and the trans isomer isomerizes to the cis isomer in this particular case. So the initially formed trans isomer undergoes photochemical isomerization to give the cis product, which is the final product in this particular case. This is again a true example of a 4pi cycloaddition reaction, presumably involving the formation of an exciplex. That is, initially the photoexcitation of anthracene results in the formation of the singlet excited state of anthracene. The singlet excited state of anthracene forms a pi complex with the transoid butadiene in this particular case, forming an exciplex kind of a molecule. The exciplex intermediate is what is actually undergoing the cycloaddition reaction to give this initial trans adduct, which isomerizes to the cis adduct during the course of the photochemical isomerization reaction. The more common reaction that one observes in the laboratory is the dimerization of anthracene. Anthracines are very reactive in the 9 and 10 position. Upon photochemical excitation, they do undergo 4pi cycloaddition reaction in a superficial manner. Anthracene itself undergoes the cycloaddition reaction to give the photodimer of anthracene, the structure of which is shown here. However, if you take substituted anthracene, there are two possible products that can be formed depending upon the relative orientation of the two molecules that undergo the cycloaddition process. The two molecules can be oriented in such a way that the R group of one molecule and R group of another molecule can be cis or eclipsing with respect to each other during the transition state. That would form the head-to-head dimer. On the other hand, the molecule can orient such a way that one molecule with the R group up, another molecule with the R group down, which will result in the formation of a head-to-tail dimer. So whether the molecules orient head-to-head with respect to the R group or head-to-tail with respect to the R group will ensure the formation of the head-to-head isomer or the head-to-tail isomer of this cycloaddition process. Now this is again an intermolecular version of the 4pi cycloaddition reaction involving a suprafacial overlap which obeys the Woodward-Hoffmann rule. When the two anthracene units are tied up with a long chain, the long chain can be anywhere from 6 to 8 carbon atoms in this particular case. The minimum number of carbon atoms that is necessary is 2 carbon atoms in this particular instance. Here the involvement of excimer is possible, excited state of one anthracene unit with the neighboring anthracene unit forming a complex in the excited state resulting in the formation of an excimer may be a intermediate stage before the product is actually formed. You can see here the bridge is essentially forming a cycle here. This is possible only as a head-to-head dimerization because of the linking methylene groups in this particular instance, resulting in the formation of a very interesting photodimer of this particular anthracene derivative, dianthracene derivative. Alpha pyrones and alpha pyridones are also known to undergo 4pi cycloaddition reaction. They do so by means of head-to-tail orientation, resulting in the formation of centrosymmetric dimer. These dimers have a center of symmetry which is the center of this molecule that is shown here. Similarly, this molecule has a center of symmetry which is the center of this molecule in this particular instance. The photodimerization of pyridone gives this photodimer by a head-to-tail orientation of the two units of the pyridone. Similarly, the case of pyrone also, the head-to-tail orientation of the two units of pyrone, alpha pyrone, results in the formation of this bis-lactone that is shown in the structure which is center of symmetry. Example of 10 electron cyclization is also known. This is between tropone and pentadiene, cyclopentadiene for example. The tropone is a 6 electron pi system, whereas cyclopentadiene is a 4 electron pi system. The 4pi+6pi cycloaddition of cyclopentadiene with tropone is what is shown to yield this particular product, which is a carbonyl bridged bicyclic compound, tricyclic compound of this nature, for example. Please note that this reaction is completely exoselective in the sense the pi system is exo to the bridging methylene unit. In other words, this carbonyl pi system is endo to the bridging pi unit. This is unlike the Diels-Alder reaction, which predominantly undergo endoselective Diels-Alder reaction because of the secondary orbital interaction. Here the secondary orbital interactions are unfavorable to form the endo-adduct, therefore it forms the exo-adduct, which is explained in the next slide. If you consider, for example, the Diels-Alder reaction between the cyclopentadiene and maleic anhydride, the secondary orbital interactions are generally bonding in nature. On the other hand, if you take tropone and cyclopentadiene to undergo a 6pi/4pi cycloaddition reaction, this is the primary interaction between these two carbons, carbon number 1 and 4 of the cyclopentadiene and carbon number 1 and 7 of the tropone, carbon number 1 and 6 of the tropone, for example. This primary interaction essentially leads to the sigma bond formation, but in the endo approach, if you see, the secondary orbital interaction is an unfavorable antibonding type of an interaction. Such an antibonding type of an interaction in the transition state will essentially destabilize the transition state. Moreover, the endo approach is actually a sterically hindered approach. It doesn't have the thermodynamic stability of the secondary orbital interaction. However, in the exo approach, such a secondary orbital interaction does not exist. So this is likely to be both from the steric point of view as well as from the thermodynamics point of stability point of view. This is a more favorable transition state, and that is the reason this exo adduct is formed in this case of 6pi 4pi cycloaddition reaction. Unlike, for example, in the 4pi 2pi cycloaddition reaction, where endo is favorable because of the secondary orbital interactions being bonding type of an interaction. This is an essential difference between the Diels-Alder reaction and the higher order cycloaddition reaction. The same type of reaction is also seen in the case of the fulvalene, which is this molecule here. This fulvene molecule undergoing a cycloaddition reaction with the tropone. Again, an exostereochemistry is what is observed with respect to the bridge that is shown here. This pi system is exo for the identical reason that we discussed earlier with the tropone and the cyclopentadiene. So the exo isomer is a more favorable isomer in the case of the 4pi 6pi cycloaddition reaction in this case. Now, cycloaddition reaction of this kind of azapine is very well known. Azapine undergoes a cycloaddition reaction to give two possible products. The one product that is shown here is a 6pi 4pi cycloaddition reaction, which is this particular reaction. This reaction essentially produces a 4pi 4pi cycloaddition reaction, 6pi 6pi cycloaddition reaction, which would correspond to this particular adduct, a 4pi 6pi cycloaddition reaction which would correspond to this particular adduct. The initially formed 4pi 6pi cycloaddition reaction under the reaction condition undergoes a 1,3 thermal shift, 1,3 carbon shift. If you consider this carbon-carbon bond, this can undergo a 1,3 shift to this particular carbon with a concomitant migration of this double bond to the next position, resulting in the formation of a 6pi 6pi cycloaddition product. So the reaction involves, there are two reactions that are involved. The initially formed 6pi 4pi cycloaddition adduct is this particular adduct. This undergoes a thermal migration to give a 6pi 6pi, formally a 6pi 6pi type of a cycloaddition product, which is this centrosymmetric molecule that is shown in this particular case. Here is a higher order cycloaddition reaction of the type 8pi 2pi cycloaddition reaction. If you consider this molecule here, this can undergo a cycloaddition reaction involving all the 8 pi electrons in this particular system with the 2 pi electrons of the dimethylacetylene dicarboxylic acid, resulting in the formation of a 8pi 2pi cycloadduct, which is a 10 electron cycloadduct. Under thermal condition, this should be suprafacial in nature because it is a 4n+2 system according to the Woodward-Hoffmann rule. A 4n+2 system under thermal conditions will undergo a suprafacial cycloaddition reaction. How do we know that it is suprafacial on both components? From the acetylene component, you cannot tell whether it is suprafacial or not because there is no stereochemical center. However, from the 8 pi electron system, because these two hydrogens are cis with respect to each other, these two hydrogens we are talking about, cis with respect to each other, one can very clearly tell that the 8 pi component has also been a suprafacial component in this particular case. Under the reaction competition, it undergoes aromatization by loss of hydrogen undergoes oxidation by loss of hydrogen to give this fully aromatic system as the final product during the course of the cycloaddition process. Dihydroacylene is formed during the cycloaddition reaction of this exomethylene cycloheptatriene with the dimethylacetylene dicarboxylic acid. Here again the cycloaddition is between this carbon here and this carbon here to form a 5-membered ring. So all the 8 electrons of the exomethylene cycloheptatriene is involved along with the 2 electrons of the dimethylacetylene dicarboxylic acid, resulting in the formation of the dihydroacylene derivative, which is this particular derivative. In the case of this reaction here, this is also an example of an 8pi 2pi cycloaddition reaction involving a suprafacial overlap. Here dimethylacetylene diazido dicarboxylate, dimethyl diazido dicarboxylate is what is used as the component of the cycloaddition partner. Here the reaction essentially proceeds between this carbon over here and this carbon over here, resulting in the formation of a bridged bicyclic system of this type, and the cycloaddition of dimethyl diazido dicarboxylate to form 2,5,7-dimethylene cycloheptadiene is what is illustrated as a 10 electron system in this particular case. These are interesting examples of higher order cycloaddition reactions involving 10 electron, which is a 4n plus 2 system, involving a superficial overlap of the superficial overlap of the two components. However, there are no stereochemical centers to ascertain whether it actually underwent a superficial cycloaddition reaction. We conclude that it could be superficial addition reaction by analogy to the other known 8 plus 2 cycloaddition reactions, which are similar to the Diels-Alder reaction involving 4n plus 2 electron system. This is one of the largest cycloaddition reaction that is known in terms of the number of pi electrons involved. You can see here there are 14 pi electrons in the heptafulvalene. Heptafulvalene molecule is this one, and it undergoes cycloaddition reaction with the tetracyanoethylene. All the 14 electrons of the heptafulvalene is involved, as you can see from the rearrangement of the pi electron system during the course of the cycloaddition reaction. The cycloaddition occurs between this carbon and this carbon of the heptafulvalene and these two carbons of the tetracyanoethylene, and the reaction is very clearly antifacial with respect to the larger pi system. This is a 4n electron system involving totally a 16 electron species. So one of the component has to be an antifacial component according to the Woodward-Oppen rule. It is that the larger pi system, which has more flexibility, is the one that can undergo the antifacial component of this particular reaction. This is a 2 pi electron system, which is a superficial component, and this is a 14 pi electron system, which is an antifacial component. The geometry of the molecule is such that this is a twisted compound. These two carbons can easily overlap in an antifacial manner with the tetracyanoethylene. In other words, very similar to the perpendicular approach is what is happening in the molecule in terms of the geometry of the molecule favoring the antifacial addition reaction. How do we know that it is an antifacial addition reaction? Whenever a molecule is undergoing an antifacial addition reaction, there will be an inversion of stereochemistry. So these two hydrogens which are pointing out now should have been cis with respect to each other if it was a superficial component, but the stereochemistry crystal structure of this molecule shows very clearly the stereochemistry to be the trans stereochemistry. The trans stereochemistry can arise only if this component had undergone an antifacial type of a cycloaddition reaction with this as a superficial type of a cycloaddition partner. So overall, this is a 14 pi antifacial and 2 pi superficial involving a 16 electron, in other words a 4n electron system undergoing a cycloaddition reaction to give this particular product. I hope you enjoyed the higher order cycloaddition reaction. These are very interesting examples of multiple electron systems. More than 6 electron system is what we have considered in this module. Thank you very much for your kind attention.